Up until now, we've always talked about direct current, so we have a voltage source that is constant. Now we're going to be talking about alternate current. This is what you actually have coming out of the walls every single day. This is something that's going to oscillate. So there's going to be a voltage source, but it oscillates as a sine or cosine function. We're going to start out by examining what that looks like, and then we're going to example a system that just has a resistor, a system that just has a capacitor, a system that just has an inductor, and then a system that has all three. Your book likes to do all of this in terms of phasors. I was never taught phasors in math, so I'm just going to rely on the sine and cosine function. I highly suggest that you follow along in your book when we're going over the resistive load and then in the next video the capacitive load, because you want to see how those sine and cosine functions change with each other, because there's going to be some kind of phase constant to relate the maximum voltage and the maximum amount of charge. Okay? I know that's a lot, but let's bear with it. Okay, so an alternating current. What we have is we have some voltage. Again, we're going to use the outdated term EMF, so that's a capital cursive E right there, is equal to some maximum amount of voltage times sine of omega dt. That d is a subscript right there. I'm going to explain what that is here in a second, okay? So this thing is obviously oscillating because we know the sine function oscillates. The current inside of our alternating current circuit is going to be, as a function of time, capital I standing for the amplitude of the current, sine of omega dt, again subscript on the d, time minus a phase constant phi. We're going to do a lot of analysis on that phase constant here in a couple of seconds. Okay, so Em is the amplitude of EMF. So that's the maximum amount of voltage that we are going to feel, okay? Omega d is going to be our driving angular frequency, okay? Remember that we want to handle something inside of there, some kind of angular frequency term. If we think about this as the spring block system, that's going to be what's driving our whole system right there, okay? Omega dt, so the term omega d multiplied by t, is known as the phase, okay? So that tells us the phase of the circuit, omega d multiplied by t. I stands for the amplitude, and then phi is our phase constant. So this is going to tell us whether or not the current is a maximum as the exact same voltage maximum. What we're going to find is that in different circuits, sometimes the maximum voltage is the maximum current as well. They happen at the exact same time, and sometimes we're going to find that they're out of phase. Okay, so let's take a look at a resistive load. Start nice and easy. First, we need our alternating current source. In a circuit, that stands for our alternating current source. This is a circle with a little squiggly line inside of it, okay? We're going to hook that up to a resistor, okay? So we have some resistor here. This is our alternating current source. This looks similar to what we were doing before with a constant voltage source for our direct currents. It's not going to be exactly the same thing, but we're going to use exactly the same principles as we do this sort of thing, okay? So there's obviously going to be some kind of voltage on the resistor. There's some voltage on the resistor, okay? If I go completely around the loop, the same rules apply from direct current examples. So the total voltage, if I go completely around the loop, must be, dramatic pause, 0. It has to be 0, okay? So, in order for that to happen, then I must have the voltage source from the AC source. Notice I'm using it over here and it's going to oscillate, minus the voltage drop from the resistor. The total voltage must be equal to 0. So all I did was go around the loop. I have a voltage gain by going over the AC source, and then I have a voltage drop by going through the resistor. Okay? Now, what that means is that the voltage across the resistor must be equal to the AC source, correct? All I'm doing is I'm just using that 0, and I get that the voltage across the resistor must be equal to the AC source. If that's true, then that means that the voltage of the resistor is equal to capital EM sine omega dt times, well, just sine of omega dt. I was thinking I was going to do a phase constant there, but whatever, okay? So the voltage must be equal to the maximum amount of voltage, the amplitude of the voltage, sine of omega dt, okay? So that must mean that VR is equal to EM, so we're going to define some kind of voltage. Notice I'm using a capital V here. I'm going to define a voltage amplitude across the resistor, and that is going to be equal to the amplitude of the voltage from the AC source. And so now what that means is I can rewrite this guy as VR. So the voltage of the resistor as a function of time is equal to capital VR sine of omega dt. Okay? This doesn't seem very necessary right now. I understand that this seems like, well, duh, but it's going to come into play when we do it for the capacitors and the inductors. Okay? So right now what I have is that the voltage across the resistor as a function of time is equal to some maximum amount of voltage sine of omega dt. Pause, make sure you got this in your notes. I'm going to switch over to the other whiteboard. Okie dokie. Whoa. Okay. Now let's take a look at the current across the resistor. The current across the resistor. The current would be equal to the voltage across the resistor divided by the resistance. So if I replace the voltage in the resistor with what I just had, that's going to be the amplitude of the voltage divided by the resistance, the sine of omega dt. Okay? Now I can rewrite this as a current amplitude, and so now what I have is that the current is equal to a current amplitude IR, because what I'm doing here is I'm saying VR over R is equal to a current amplitude. The current amplitude across the resistor, the sine of omega dt, and then I remind myself from the previous whiteboard, there has to be a phase constant here. Now notice that they both have the sine function. Okay, the voltage has the sine function and the current has the sine function. So what that means is that we have a maximum amount of voltage at the same time we have a maximum amount of current. So the phase angle here is actually going to be 0. The phase constant is 0 because I'm using the sine function here. It should be pretty obvious that when I do the capacitor, I'm going to be taking the derivative in order to get the current, and that derivative is going to create a cosine function, so that's going to change the phase constant. But for right now, for the resistive load, that's very straightforward. What we end up getting is that the voltage across the resistor is equal to the current amplitude across the resistor times the resistance. So yeah, it's V equals IR again. So for the resistive load, we get the exact same equation, the exact same relationship. Because they're both in phase, the current and the AC oscillation are both in phase, we end up getting the exact same Ohm's law representation. It's not going to be the case when we do the capacitive load and the inductive load, so I would recommend taking a deep breath before we go on to that.